The live stream today, I thought I'd share awesome premiere today with our old live stream we had. This is a great presentation done by Andrew Johnston where he proves it's measured flat. Enjoy.
Yeah, good day, mate.
Yep, so just watching on YouTube, just interested to see how long that's... There we go, it's a few seconds behind, that's not a problem. Okay, good. Off we go. G'day. If you haven't picked up, I'm Australian, so halfway around the world from you, Flatzoid. And welcome to my presentation. Eduardo's evidence of excess. Now, why Eduardo? Well, I've been blocked from your channel quite a few times, and my username has changed many times. Currently, I am Eduardo. Eduardo Igarisu number 6, and so Eduardo is will be presenting this presentation. Just checking, is that coming through okay?
Yeah, it's fine when you are. I see Michael's trying to talk. So, Michael, you might just have to mute, mate. Sorry.
Yeah, I was just hearing a little bit of sound coming through there. Yeah.
But I hear you perfect. Okay.
Fantastic. All right. Well, I shall plow on then. Okay. So Eduardo's evidence of excess. So actually, whoops. Let's go back one. So I'm presenting about geodetic surveying and the evidence it has for the spherical Earth, and that is using the measurement of spherical excess as evidence. I've got 3 main arguments. One, that there is empirical measurement of spherical excess in geodetic surveying. I will show analysis that refutes the flat Earth arguments, which I've heard about geodetic surveying, that being that the surveyors actually measure a flat Earth and then add in the curve to make it look like it's a globe. And lastly, that the predictions that they make in their survey using the assumption of curve match real-world measurements. Okay, my main reference will be the transcontinental triangulation and the American arc of the parallel by the US Coast and Geodetic Survey. This was, as the name suggests, highlighted there in red, a geodetic survey across the full width of the North American continent, roughly following the 39 north latitude line. The principal field work was done between 1872 and 1898, and the book, The Results, was published in 1901. Now, I'm going to put this in the context of the knowledge of the shape of the Earth at the time, and we'll just go through a very brief history of that, which a lot of you will probably already know, but we'll run through it. The spherical shape of the Earth was surmised by the Greeks since at least the 5th century BC, and we're all probably well familiar with Eratosthenes and his sticks and shadows around 240 BC. About 150 years later, another Greek called Posidonius did something similar using 2 locations in Greece, using the star Canopus. At his northern location in Greece, Canopus barely rises above the southern horizon, and at his southern location, it reaches a higher altitude in the sky at night. And so, just like Eratosthenes, he had deduced his latitude distance and compared it to the distance over the ground to estimate the circumference of the Earth. Just as a side note, you might think, well, why didn't he use Polaris to determine his latitude distance like we might do today? Well, 2,000 years ago, Polaris wasn't the pole star. The pole star does move, and in fact, at the time, there were no bright stars within about 8 degrees of the northern celestial pole. So he didn't have a pole star like we do today. The globe model, of course, has an explanation for the precession of the equinoxes. I haven't heard anything from the flat Earth side about this one, but that's just a side note. Now, moving on quite a bit, we're probably all familiar with Al-Biruni, who in about 1000 AD used horizon dip to measure the circumference of the Earth, came up with a similar number. In about the 1600s, with the scientific revolution, in telescopes and lenses were invented, and that led to better, more accurate measurements of the sky and of the ground. In 1670, Picard was probably the first modern accurate survey, geodetic survey, and he measured a degree of the meridian arc around Paris and calculated the radius, which these days we only disagree by about 0.5% of the radius of the Earth to what he got to. So he got pretty close. Let's see. Newton in 1689 theorized the Earth would actually be flattened at the poles due to rotation, and this was confirmed by French surveying expeditions to South America and Finland in the 1730s. And so by the time of the transcontinental triangulation, spheroidal models were at a point of only differing from current models by about 100 meters of radius. I've just plotted here some historic spheroids over time, and you can see by about the late 1800s, we haven't really changed our estimate of the size of the Earth by very much. we're in pretty strong agreement since then about the shape of the Earth. And lastly, the point of all what I've just provided to you is that the shape of the Earth was well known by the late 19th century, when the transcontinental triangulation was done. And they weren't setting out to prove the shape of the Earth, but rather they were surveying to provide a framework for accurate mapping of the entire United States. So now to triangulation survey. The purpose of surveying is to establish precise locations of points within an area. With triangulation survey, it is done by measuring an angle from two known locations on our diagram, A and B, the baseline, to a third location, and using trigonometry to determine the position of the third. And furthermore, the precisely measured baseline provides the starting point for the distance calculations. This method is well suited. Sorry, that one's a bit big. A bit better. This method is well suited to covering large areas with a modest amount of effort using long chains of triangles. And let's make that bigger again. That's a bit big and not a great picture, but using long chains of triangles to survey your territory. Okay, now the transcontinental triangulation itself covered about 4,000 kilometres between Cape May, New Jersey, which is on the east coast of America, to Point Arena, California on the west. Across the entire country, there were 308 survey points, from which they formed 743 surveying triangles. And it was broken up into 10 small base nets. These are the yellow circles in my diagram here, small areas of triangles, which were joined by 9 long chains of triangles and a few further 2 short chains to reach the ocean at both coastlines. Now, what I'm talking about being the base nets were relatively small areas of surveying. This one is one which is about 40 kilometres by 60 kilometres with a reasonably high density of survey stations. And these base nets were connected together by the long chains of triangles. So this is a chain of triangles joining 2 base nets on the left and the right of the screen. This one's about 450 kilometres long. So within the small base nets, you have a very high accuracy, and within the chains joining those base nets, you've got a little bit less accuracy, but you cover a lot of ground relatively quickly. So at each of these survey stations across the entire network, there we have some strapping young men of the Victorian era. They would set up a theodolite and measure the angles separating the surrounding stations multiple times and average those readings. For example, here in the base station I'm using, the Linstead point, which is at the centre of the base station, there are 7 surrounding stations. So they measure the angles between those 7 stations multiple times and average them. These stations commonly, in some areas, they are up on hilltops, fairly spectacular areas, so they can get a good view of the stations around them. And in the lower lying areas, they would set up observing towers. In this case, this tower, the platform about halfway up there is about 30 metres off the ground. The target at the top, when other stations are viewing back to this one, is about 80 metres off the ground. It's the sort of effort they would go to. Now, it's important to stress that when they're measuring these angles, they are just measuring the horizontal angle, or in this diagram, what's called the azimuth angle. Between targets. The vertical differences are irrelevant between targets. It doesn't matter if one target is up on the top of a hill, the other one's down below them in a valley. It is just the horizontal component of the separation that matters. Now, this importantly means that refraction is not a factor in these measurements. Now, given that refraction essentially only happens in the vertical direction, and this is actually one of the reasons why I like using spherical excess as one. It's pretty much my favourite globe evidence. Because often in these debates, refraction can become a bit of a distraction, can become a source of confusion, black swan, things like that. We all argue about refraction. So with spherical excess in geodetic surveying, we're only dealing with azimuth angles. So we don't even need to consider refraction as a factor in those measurements. Okay, so at each of the base nets, they also have one line which they meticulously measured the actual length across the ground. In the base net I'm showing here, I've highlighted that with a red line down in the bottom right of it. Now, the measurement for each of these base stations took quite a bit of effort. They first had to clear a direct path between those 2 locations. Fair bit of effort there. And then using measuring rods, they would measure that distance. This one actually for the base net that I've just showed you, they used a set of 4 measuring rods, some precisely measured rods of about nominally 2 meters long each. These rods have been compared to national standards, so they knew the exact length of these rods right down to fractions of a millimeter. And throughout the surveying process, they would actually record temperatures when they were doing the measurements, so they could account for the thermal expansion of the rods. Okay, now, and here we have a bit of an example, a bit of a painting at the time of them actually using the rods, just end over end, adding one to the other, and meticulously measuring the length of that baseline. The Kent Island baseline, the one I've just been showing, is about 8.5 kilometres long. It took them over a month to measure, and they calculated the length down to the 10th of a millimetre over an 8.5 kilometre length. The longest baseline in the whole survey was actually over 17 kilometres, so about the same sort of size in general terms, and it took 2 months to measure that baseline, and some of them actually, they measured forwards and reverse in both directions twice, so they actually measured them 4 times to make sure they had them accurately measured. From all this effort that it took to do this, you can understand why that simply measuring your way across the country to determine where you're located is a phenomenally impractical and slow method to do things, and that's why triangulation survey is used, where you can jump large distance just with optical measurements. Okay, so on to what part of the survey that I think is important, and that is spherical excess. So once you've got your baselines measured, your angles are measured, we come to solving of the triangles to join all those things together, and this is where spherical excess turns up. So now, hopefully most of you are aware the internal angles of a normal triangle sum to 180 degrees. But as you may also be aware, triangles can also be formed on the surface of a sphere. These are known, obviously, as spherical triangles. Their internal angles always add up to more than 180 degrees. And as they increase in size and take up more of the surface of the sphere, the angles can add up to as much as 540 degrees. And the amount that they add up to over 180 degrees is known as the spherical excess. And in practice, we won't be dealing with huge amounts of spherical excess. We're dealing with fractions of a degree in the case of this surveying. So now I'll move on. Now, the globe claim about spherical excess is often put simply as triangles are surveyed and found to have spherical excess. Well, unfortunately, the reality of surveying is it's not quite so simple out here in the real world. So again, looking at this Kent Island base net that I'm going to use as an example, we'll look at the first this triangle that I've highlighted between Kent Island South, Kent Island North, and Taylor. Okay, now these are the measurements as published in the publication. Now, the thing I need you to look at is the green box over here in the top left. Actually, yes, my cursor is showing, so I can show you. That didn't work. Hang on a moment. There we go. I got my highlighter going. So we can look over here in the green box here, and we can see that the angles of the Kent Island triangle, the one I was talking about here, add up to 180 degrees, 0 arc minutes, and 1.29 arc seconds. So we see that it does indeed add up to slightly greater than 180 degrees. But if we look down the page, we see, for example, triangle 2, triangle 3, and triangle 5 add up to a little bit less than 180 degrees. Okay, which is a little bit of a problem. So you might think that this just makes the measurements a little bit inconclusive, a bit of margin of error, maybe. But there is actually a big problem if you think these angles are accurate, because planar triangles, flat normal triangles, sum to 180 degrees. Spherical triangles always sum to greater than 80 degrees. So how can we have triangles that add to less than 180 degrees? Now, I'll get to this explanation in a moment, but we're going to shift to somewhere else where this isn't quite so much of a problem. So just briefly before we go, if we look over here on the right of the screen, you'll see the distance of the sides of these triangles. It's in meters. So if we look at this first section, we've got 8, 13, and 11 kilometers. So there's a modestly sized triangles in terms of geodetic surveying. But if we move over to, there we go. So I'm now showing similar things for the Salt Lake area. So Salt Lake, Utah. We're getting to the edge of the Rocky Mountains here. And if we look at the right-hand side here, we can see the triangles on this side have sides here of up to 185 kilometers. So they are significantly larger in this case. Okay, I can see my cursor highlights not coming through. It doesn't matter. I shall plow on. Okay, so now looking at the Salt Lake basenet triangles with these big triangles, if we look at the red boxes on the left, I've highlighted again with little red boxes there, we can see that they have spherical excesses from these measurements of 6, 13, 33, 11, and 35 arc seconds. None of them have a deficit. We all have an excess of angles in those triangles. So we find that once the triangles become large enough, we have clear empirical measurements of spherical excess. And that is my first argument. So now moving on to the explanation, what is going on with the Kent Island triangles? The problem is that there's no such thing as a perfect measurement. For these smaller triangles, the amount of excess is fairly small and it could be hidden by the errors in the angle measurements. But there's a way to reduce that error. It's called observation adjustment, and it's a common process in many types of surveying. Yes, geodetic and even planar surveying does this to error correct, basically. So, for example, say we have measured 4 lines from locations, and they're all pointing to a point at the top of this picture, to a point we're trying to measure called point P. But if we zoom in to where those lines are all converging, we find that they actually don't converge. Because of small errors in the measurements, when we plot them out, they're not converging. So what do? We have 6 different locations where these converge. Where is point P? Is it one of those? No, we don't really know. So what we do is we find an average, some sort of average of those locations, and that's that cross in the middle of the screen. And then we adjust those angles that we've measured so that all our 4 lines actually converge at the same point. Now, we still don't know the actual location of P, but this is statistically what is known as our most probable location. From all the data we've got, this is the best we can determine and say this is where point P is. So this is what's done in geodetic surveying to correct for errors as such. Now, they don't do it one point at a time and then move on to another point, because that will actually allow for propagation of error. They actually look at the entire network or an entire group of triangles and solve the whole lot at once. Now, these days, you would quite easily take all your data from your observations and have a computer do the calculation, and it would probably do it quicker than Don Pettit would go back to the moon. But in the 19th century, it all had to be done by hand. The transcontinental triangulation used a method from this book, the Treatise of the Adjustment of Observations, in 1884, which itself is based on a mathematical process called the least squares regression analysis. Needless to say, the method is quite involved, but it is just a mathematical way of averaging all your observations and minimizing the total amount of error across your entire network. Now, importantly, I do have to mention that these corrections do not actually add any angles. They just shift them around. So looking here at the angles that were measured at the Kent Island North base, in the red, we can see the angle difference between the different stations around that they measured. In the orange box, we can see the corrections that were made to these due to this statistical process. And in the blue box, we see what the angles got adjusted to. And if you look at the orange box, if you add up all those various small pluses and minuses, they add to 0. So they're not actually adding any angle to which might be an accusation of them. They are just shifting those observations around ever so slightly. Okay, moving on. So if we now look back at the Kent Island triangles, which is the screen I had earlier on, we can see that in the red box down the middle of the screen, these are the corrections that are made to each of the angles, each of the triangles. And we can see we have a little -1 arc second, we will have plus 0.6 of an arc second, etc., etc. And so the triangles which we had trouble with before, being I think it was 2, 4, and 5, 2, 3, and 5, they have had some corrections made. And so in the blue, we now see that every single one of these triangles now has a very small amount of excess in it. So everything's good now from now on. And if we go back to the Salt Lake triangles, which were the really big ones before, which already had excess, which is these small red boxes, we find in the big red boxes, we have the adjustments that are made to them, again, around about up plus or minus 1 arc second or so to each of those. So there's still only very small adjustments. And highlighted in the blue, we have their corrected angles and the amount of spherical excess, and we still find that we have quite a significant large amount of spherical excess, 7, 14, 31 arc seconds of excess. So now that we've done the corrections to the angles, we can calculate the distance between the points and therefore give locations for all those surveying points using trigonometry. Okay, now moving on to my second argument, I've often heard the claim by flat earthers and others that geodetic surveyors measure flat and add curve. Well, I've just shown you in those observations just before that they don't actually measure flat. If the triangles are big enough, they're not measured flat. They do have curve. But now I'll show that also, that even with these corrections, there's not really any evidence to say that they add curve. Now, just as with planar triangles, if we know some of the properties of a spherical triangle, we can solve for the rest of the properties of the triangle, and that includes the radius of curvature that the triangle is taken from. Now, MC Toon created this lovely spreadsheet using some of the data from the triangles in the survey. He's got data there for 43 of the triangles in the survey and was able to put them through the equations and calculate the radius of curvature for all 129 triangle sides separately, because you can do this for each side of the triangle separately. And if we look at the results of that, I've highlighted there in boxes down to 1 to 10. These are, for example, next to 1, that is the 3 sides of triangle number 1 in the spreadsheet. And below it is the 3 sides of triangle 2, 3 sides of triangle 3, etc. So we can see with triangle 1, within the triangle, the 3 sides all come up to a radius value, this is in meters, that is pretty consistent with each other. If we look at triangle 2, the radius values here for each 3 sides of the triangle, pretty much the same value, same for triangle 3. But between each of those 3 triangles, and I've averaged each triangle here on the right in the blue, you can see that the values do actually differ by a little bit. And you can sort of expect some of that due to errors of measurement, errors of calculations. They're doing this stuff by hand. However, if we plot these values, the blue values here, for all 43 triangles, and I've just laid them out here in numerical increasing order, we see that there's a spread of values. Most of the values are fairly close to an average value across the middle of the graph here, but we see that there are some that are a couple of percent below that value, and over at the right side, we see some that are a couple of percent and up to, I think it's about 5% above for that. And that's only 43 of the triangles, but it is indicative that they do vary in their radius value. Now, incidentally, the black line I've put is not the average of those values. The black line is actually the expected radius value based on their WGS84 spheroid. So you can see that their calculations that they got on average seem to compare very favorably with what we would expect today with our knowledge of the shape of the Earth. So the conclusion of this, being a spread of values and not all sitting nicely about an average, is if the surveyors actually were taking flat measurements of flat triangles and adding in the amount of spherical excess they are told to expect from a spherical Earth, they did a bit of a sloppy job of it. Because if they had actually done this as a backwards calculation, we should see this radius value vary by a whole lot less. It should pretty much be very consistent, and it's not. Now, I did a second analysis of some of these triangles that showed a very similar thing. One of the other properties of a spherical triangle is that the amount of excess is linearly proportional to its size. The bigger it gets, the greater the amount of spherical excess. So I took 15 triangles, 5 from the Kent Island area, which was in Maryland on the East Coast, 5 from Salina area in Kansas, which is right in the middle of the country, and 5 from the Salt Lake area, which is in the Rockies, where you've got big triangles, you've got mountainous terrain, so it might be a little bit different conditions there, and compared their excess to the area. So on the x-axis of this graph, we have the area of the 15 triangles that I chose, not quite randomly, but a selection. And on the y-axis, we see the amount of excess in arc seconds that each of those triangles exhibits. And as you can see, there is something of a linear relationship going on there. You might think, well, that's what we expect. That's great. But if we actually look a little bit closer with it, and we look at the rate of excess per area, we find that maybe not for the large triangles, but again on the left side, we see for some of these small triangles, there's a lot of variation in the rate of excess. That is the amount of excess per area of triangle, and we see that there's a lot of variation. So again, if the surveyors had actually taken flat measurements and back calculated and add in the expected amount of excess, this graph shouldn't show nearly as much variation. The numbers should be a lot more consistent. Incidentally, based on WGS 84, I haven't put the line in, but the expected value rate of excess is around about 196 based on current models. So their numbers were close to current values, but there's a bit of variation around it. And so that's my second argument, that if you look at the data, you see that there's no evidence that they back calculated expected values into it. Okay. And my last of my main arguments is some analysis that the survey themselves did to report on the accuracy of the work. It's called baseline accord. Okay, not that type of base accord. Thank you, Keith. Thank you. Sorry, Flatzoid. Thank you for the laugh there. I knew you'd enjoy the car. So I'll explain what baseline accord is. So remembering that the survey was a series of connected base nets, that's the yellow circles, and each base net had just one meticulously measured baseline. So there's only 10 actual on-the-ground measurements of length made across the entire 4,000 kilometres. The baseline accord is to see how well the measured length of one of these baselines matches the calculated length of that baseline as determined by traversing across the country from the neighbouring baseline. Okay, so I'll explain a bit more what I mean by that. So here is the easternmost triangle. Actually, I'll go back and show it. So we're dealing with this here on the east coast between the Kent Island in Maryland and St Albans, West Virginia, I think, base net. So we're dealing with this area on the close to the east coast. So over here, on the right in orange, we have the Kent Island base net. And over on the left, we have the St Albans base net. And in between, we have this huge connected series of triangles. Now, this spans about 450 kilometres between the left and the right of the screen. So if you consider the hypothetical situation of the surveyors starting over here at the Kent Island base net and measuring this very small, thick line here, which is about 8.5 kilometres long. And then they traverse all the way across the country to the west here, over 450 kilometres. And all they're doing is taking angle measurements along the way. They're not doing any measurement of the length of the ground anywhere at all. And they get over here to St Albans, and I'm going to zoom in on the St Albans area, and they get to this point where they've surveyed all these except for these last two, which I've circled in orange here. So they stop at this point, and using the angles that they've measured along the way, and that one baseline that was of 8.5 kilometres that was measured 450 kilometres away, they calculate how far apart these two locations are, or how far apart they think they are based on their surveying. They do the statistical corrections and they apply the trigonometry and they come up with an answer. And in this case, they would come up with an answer of 3,870.4126 metres for the separation of those two locations. Okay. Meanwhile, whilst they've been coming across the country doing their angle measurements, they've had another crew out actually physically measuring the distance between those two locations. And that crew come back to them and they report that they reckon that the distance that's actually measured is 3,870.4028 metres for that length. So if it's not clear, after the surveyors traversed 450 kilometres just taking angle measurements, their calculation of the separation of those two locations was within 1 centimetre of the actual measured length, which is pretty amazing. So now this shows that their angle measuring, their correction techniques and their trigonometry were really, really accurate. But I hear you, how is this evidence for a spherical Earth? Couldn't this all just be trigonometry being done on a flat plane, matching the distances on a flat plane? Well, no. The reason being that the methods used to solve the triangles to get themselves across the country use spherical trigonometry, not planar trigonometry, which has in it an assumption of the radius of the Earth into the process. So doesn't that mean they assumed the radius to determine the radius? Well, no, that's also not true. In the example here that I've just shown you, the calculated length of the St Albans baseline here on the left of the picture was essentially a prediction made from being 450 kilometres away. the fact that their prediction was based on an assumed radius, as they came across, and the geometry of a spherical surface using spherical trigonometry, and got such an accurate answer, is pretty strong evidence that the surface they actually traversed across is actually spherical. It's kind of like the difference of whether they used a chord length or an arc length to calculate their movement across the country of that 450 kilometres. They made their predictions based on using arc length, assuming it was an arc length, and got within a centimetre of this distance, 450 kilometres away. So this is pretty strong evidence, again, that the distances across the surface of the Earth really are arc lengths. And that's my third point. So that's my 3 main points. Quick summary. Empirical measurements of spherical excess. So here in the Salt Lake BaseNet, this is a picture I showed you earlier on, we can see in orange and then in the smaller red squares, we even before doing corrections for margin of error, we see that we do have excess angle in those triangles. Secondly, some analysis that refutes the measure flat and add curve argument, and that was the, sorry, just get myself in the right place again, showing on the left, showing variation in the curvature, the effective radius of those triangles. They were not all consistent. And on the right, we showed variation in the rate of excess in those triangles. Again, if they'd been calculated back, the plot of these data should be much closer together. Okay, and lastly, the accuracy of their spherical predictions, which I've just shown a second ago, that using spherical-based calculations for the distance across the chain of triangles, they were able to make highly accurate predictions of the separation of two surveying points that were hundreds of kilometres away from where they started. So that concludes my main argument. Sorry, let's go on from that. But I'm not finished yet. Another thing. So if you somehow think that if somehow after the evidence I presented from the publication and the analysis that I've done, you still think that the people involved in the survey are somehow still hiding the reality of the flat Earth, then you need to realise that this is just one survey of quite a lot that were done. Triangulation surveys were commonplace for over about 250 years, and really only since about the mid to late 20th century have they fallen out of favour for different techniques. So over that 250-year period, here are just a smattering of other surveys, which you'd also have to prove are being lied about. Here is the principal triangulation of Britain done between 1791 and 1853, the Great Trigonometrical Survey of India between 1802 and 1871, which very famously was the first determination of the height of Mount Everest, which was done in 1847. So is that wrong, is the question. Here is France's situation between 1818 and 1843. Flatzoid, if you look carefully, it's a bit hard to see. You might recognise this area of the world. This is Southern Africa, including South Africa and Zimbabwe. That was their situation between 1883 and 1953 of the surveys that had been done over about a 50, 60-year period. We have Japan in the 50s in the post-war period. We have the sum total of all geodetic surveying in North America as at 1969. We have somewhere I like, Australia as at 1986. We have a more detailed view of the US as at 1983. And lastly, I don't have a date for this one, probably the 60s, maybe the 70s. We have the sum total of all geodetic surveying, horizontal control surveys done across the entire globe in around by about the 1960s. That's a lot of surveying, and we have actually, if I just, can I zoom in here? Yes, I can. We have a little bit of a bonus here for flat earthers. Over here in the right-hand corner, we can see that even parts of Antarctica had been surveyed by then. I'm not sure what, whoops, wrong button. Not sure what you think about that. Okay, so I will just about finished here. So, question is, if this is actually all one massive conspiracy, and then if you consider all the people that are involved in all those centuries of surveying, then why is it that flat earthers cannot cite anyone that has come forward and even hinted that it was all one big elaborate ruse? That no one has said that they have seen the very, very simple fact that the angles that they helped measure and record do only indeed add up to 180 degrees. And why don't we hear citations of anyone who's published their own independent surveying that proves that the official ones are wrong and just a lie? And, no one is stopping you from going out there and doing your own surveying and exposing this lie. So the question is, why don't we hear about these things? Is perhaps geodetic surveying actually true? Okay, final thoughts. Now, I don't expect to change your mind here, and that's fine. But I've been reading up about this thing, this subject. I thought I'd like to make a presentation and present to you that some of the assertions that I hear from flat earthers about surveying and spherical excess are refuted by the data in this publication and also my analysis of the data. That the survey's empirical measurement of spherical excess and thus curvature and its predictions based on assumption of curvature are in complete accord with the known shape of the Earth. So that's it. I'm done. I hope I didn't go on that much longer. Thank you for coming to my TED Talk. And that's it. Thanks for listening to Eduardo.
Thank you, Eduardo, Andrew. Before we get started, I just say Alan Norton did send a $2 super chat. He says, Andrew, prove a triangle has curve.
Well, Alan, that's what I've just shown in the measurements of the angles between the vertexes of the triangle. And the one I point to mainly is the Salt Lake base net, where the triangles are up for 185 kilometers on a side. Prove it has curve. Well, those triangles have excess of 180 degrees in their internal angles. And geometrically, that is proof, because we're talking maths, we do have proof. If the angle does have more, if the triangle has more than 180 degrees, then geometrically, it has to be curved. There's no other way to happen. And it has to be a spherical curve. It's not a hyperbolic curve. It has to be spherically curved.
Okay, cool. So there's a few problems I have with that whole presentation.
Go for it, Keith. Sorry, apologies. Dr. Flatzoid. Yes, I heard you at the end of yesterday's live stream. I think you said you're going to debunk me in 10 seconds. And Michael said he was going to debunk me before he even saw my presentation. So bring it on. I'm not constrained for time here, so I'm happy to talk about this. I'm happy to talk about other subjects.
Yeah, I can take this.
I just want to say, appreciate you letting me do this presentation without interrupting me. Sometimes Globers come on and you interrupt. It's very hard for them to present. So I do thank you for doing that.
I appreciate you presenting, and thank you for bringing all your arguments.
Thank you.
I can do this in many different ways, but the first one I ask is, do you know what elliptical consideration means?
Are you trying to say that because the Earth is not a perfect sphere, it's spheroidal, there's a problem? Or is that something else you're referring to?
Do you know what elliptical consideration means?
No, I've not heard that term before.
Because that's exactly what geodetic surveying is based on. Your triangles, your spherical axis is based on the consideration that it's an ellipsoid. The WGS84 you cited is based on the Clarkson ellipsoid.
WGS is not based on Clark. WGS is a modern one. Clark did a handful in the late 1800s, and that was the one that the transcontinental triangulation used at the points where they assumed the shape of the Earth. WGS84 is based on much more modern data, and it comes out, as I've said, with a semi-major radius value of about 100 meters difference from the Clark 1880. Yes, so but I'm still not sure. I'm still not sure what you're getting at.
But it's an ellipsoid consideration. So they literally considering that there's an ellipsoid. So they take their measurements from a triangle, which is flat. Because what's a triangle?
No, a spherical triangle.
No, I'm asking what's a triangle.
Okay, a triangle is the shape formed by the shortest path between 3 points.
And those are straight lines.
They are straight lines on the surface that those points are located
on. Every triangle has 3 angles, correct?
That's correct.
And every angle is 2 straight lines meeting at a vertex.
Yes, 2 straight lines along the surface that the triangle is inscribed on.
Cool. So a spherical triangle is not actually a triangle then?
It's a spherical triangle. It's a different object, geometric object, than a planar triangle. Just like there are hyperbolic triangles, which actually have less than 180 degrees. But we won't talk about hyperbolic geometry here. There are different types of triangles. And one is called the one that we normally talk about as being a triangle is the one we experience most of the time in our ordinary life and the maths we do in school. And we call, to be specific, that is a planar triangle. And when we measure a triangle out in the real world and we are confident that it has more than 180 degrees as the sum of its angles, we know that it's not a planar triangle. We know that is a spherical triangle.
You know, there's an issue with that though, because you do know their triangles that they based on were based with theolidites based on a horizontal. You even said that the horizontal data.
Azimuth angles. They just measure azimuth angles.
Great. So it's a horizontal plane. Hence,
No. Just because you measure horizontal angles doesn't mean that the surface is horizontal and planar and flat.
They use elevation.
No. Hang on a second. If you were standing on, sorry, I'll do this one and then I'll move on to what you're about to ask. If you were standing on top of a hill and looking down all around you at locations below you, the fact that they're below you doesn't matter. The horizontal angle is just the amount you turn around while standing vertical to look at one target and turn around to, where's my hand here, and just sit on the spot, turn around and look at the and look at the other angle. It is just the horizontal turning. It doesn't matter. I mean, not on the same plane. There is no assumption that the targets you're looking at are on the same plane. Where you're standing, you have your horizontal plane that you're measuring the angle on, and there's no assumption that the other the targets are on the same plane. And by seeing that there's more than 180 degrees in the triangle, you know they're not on the same plane.
Oh yes, there is. Remember, they're just measuring slope angles.
No slope at all. Sorry,
do you know how,
Dr. Flatzoid, I need to use your correct name.
Do you know how to use how they do surveying?
Well, yes.
And it's based on planar measurements, correct?
I don't know what you mean by based on.
The geodetic surveyors come after planar measurements.
No,
that's why they link them up, because of their consideration of the ellipsoid. That's why they have their, as you put it, your triangulation links. But the baseline is based from planar measurements.
No. Well, if you're talking about the measured baseline, well, that's just a measured distance, a relatively short distance. But my first point was that in the Salt Lake BaseNet, they measured the angles of the triangles and did absolutely nothing to the measurements, and there was more than 180 degrees. In some cases, there was up to 30 arc seconds of excess in those triangles.
Okay, I just got to say, lumpy gas vacuum, $2. Andrew, SolidWorks or future period, full stop. Yeah, I'm going to show, there's a video that he linked me in Discord on that. I'm going to do it now, Lumpy, but I just got to quickly tell him that spherical axis you are talking about is slope angle underneath the horizontal. I actually debated actual surveyors on this. It's slope angle, mate.
Okay, well, I'll just put forward my assertion that when they set up their survey station and they measure the angles, they set up. Sorry, I'm going to say it wrong. Theodolites, because I can't say it right because you say it wrong. I can't get it right now. They set up their theodolites plumb for their current location, and they just measure the azimuth angles between their targets. The slope angle is not what they measure. It is simply the azimuth. No altitude angle is taken into account.
But then you don't have any spherical axis to measure.
No,
the horizontal doesn't curve, correct?
And I'm not going to get into that argument with you. It's a semantic
argument. Azimuth horizontal still has slope angles if it's measured underneath it.
No, if you had, again, you're standing on the top of a hill, or you're standing out in the middle of a field, you've got one target at the top of a hill, and you turn around, you've got the other target down in the valley. Now, if you're talking slope angle, that is the direct line between those two targets. But if you're talking, and that slope line, that sloped joining line, has two components, like geometrically. It has a vertical and a horizontal component. And in geodetic surveying, like we're doing here, we are only concerned with the horizontal. It's not the straight line between the angled line between the two of them. We are only concerned about the horizontal component of that line. That we don't look at the vertical component of it. Okay.
So you're saying it's curving left to right then?
I'm not saying any of that. I'm saying that I'm not going to get into that argument because that gets stuck
But
into
that's a
definition.
horizontal. But that's what you're saying. You're saying then it's showing a slope over the horizontal.
I'm saying the evidence that I presented was that the measurement of these triangles show that they are spherical triangles. Simple as that. More than 180 degrees, it's spherical.
You don't get it. Those angles are based on flat triangles from a horizontal. The only axis that is ever calculated, not measured, is based on the consideration that it's an ellipsoid. So they have to throw away planar surveying and stick in the consideration for the globe. That's why they have a thing called spherical axis. It's not because it's literally a sphere, it's because they believe it to be a sphere.
Now, and that's where
that's
where my first two pieces of evidence counter that. The first is that they empirically went out, just measured azimuth angles and found more than 180 degrees. And my second bit of analysis was that if they were measuring flat and adding in the expected amount of curve, then if we back and analyze it, we should find that we can extract the amount of curve that they added and find it as a consistent amount across all their calculations. And it wasn't. It was all over the place. Not all over the place.
You know why it was all over the place? You know why it was all over the place?
Margin of error of the actual measurement.
Because it's optical.
Why does that matter?
Because we're looking in three-dimensional space. It's perspective.
No.
So you've literally just debunked your whole argument because they used optical measurements and literally, remember when you said why they did the distance of arc and not the chord length? You know why that is? You know that arc length? It's based on spatial recognition of perspective.
No, that's completely misrepresenting that third piece of evidence I had. And I'll just allow me to restate. The third bit of evidence is that over distances of hundreds of kilometers, using not measuring the ground, just measuring the angular separation of all these places, that they did the calculations to join them with the assumption of sphericity and came up with actual answers that matched the length of the ground hundreds of kilometers away. If they had done those calculations based on planar triangles and planar trigonometry, they would have got a vastly different answer, and they would have traveled across the country and estimated how far apart are these two locations and got an answer that was way off what they got. So it was a test of sphericity. Is the ground between these two locations spherical? Here's the answer. If it is spherical, what do you know? It matches. Therefore, great evidence that the ground is actually spherical. Anyway, if you want to present this, go ahead.
I'm just going to quickly show this, then I'm going to tell you what I was saying. But let's quickly show this. It's from Lumpy.
Okay, yes, this is how it works. And yes, this is...
I might have to download it. Sorry, guys. You know how it goes with this.
We've helped millions of creators.
Sorry. Okay. While I'm quickly downloading that, YouTube download. Like I was saying, that spherical axis you call over the horizontal, it's done with a theodolite over the azimuth, which is a horizontal plane.
It's the local horizontal plane at the location that they take each measurement.
Great. So when they take that local horizontal measurement, it is based from, what's horizontal mean? Does horizontal curve?
Horizontal is just the location that is orthogonal to vertical.
It doesn't want to seem to work now. Yes, because we are standing in three-dimensional world, so it has to always be perpendicular to one another.
There's no reason why my horizontal plane is the same as your horizontal plane. That's the argument that's going on here. Is your horizontal plane the same as my horizontal plane? Right? And you can't assume they are. You do things, you take measurements, you make observations. Hey?
What is horizontal? As soon as you base a horizontal datum, there's no further assumptions. You've got a horizontal infinite plane, correct? You have a datum.
Okay.
No, you've got a horizontal reference.
You mentioned the phrase a horizontal datum. Now, that is an assumption in planar surveying that for the area you're surveying, everything is on the same plane. In geodetic surveying, you don't make that assumption. You do your measurements, you do your observations, and you decide whether you're on the same plane or not.
Ah, so you decide based on your belief that it's a globe.
No,
so
you decide based on the measurements.
Ignoring it's an optical measurement, using those calculations and calling it a globe. Remember my graph that I give when measuring Polaris to the equator?
Oh, don't give me that. That is just total nonsense.
That is exactly what this is proving. Thank you very much. Okay, but anyway, let's go back to this video quickly and I'll carry on.
Okay, yes, this is SolidWorks, and yes, this is a diagram of how a sextant would have to work. Okay, let's try to do this quick. This is the angle achieved by using the dip correction and the position, and here's an angle. Now, two things about the globe cutting is, yes, smart dimension is clicked over here, and we are going to try to dimension this and that. Nope, it won't let me. Cancel, said fail. All right, and then the other claim is that this is where the angle's coming from. Well, look at this. This is wrong. It's not that.
You get what he was just showing there, correct?
Well, the main problem with what Lumpy has just presented is he's talking about using sextants to measure elevation angles. I didn't mention any of that. I'm talking horizontal angles. I'm using horizontal angles, azimuth angles, as measured on the surface of the Earth with a theodolite. Different thing. I'm not dealing with elevation angles at all. Sorry,
a theodolite does angle measurements, correct? Optically.
It does angle measurements, and in the case that I've presented here is just the azimuth. Optically doesn't matter. It doesn't matter whether you're talking optical. Why does optical matter? No, it's a red herring, Flatzoid. It's a red herring to talk about optical not being valid.
It's an optical instrument, correct? So what's red herring about it? It's an optical instrument.
Yeah, and you're trying to claim that there's something wrong with optical measurements.
Is there such thing as perspective?
What does perspective change about azimuth angles?
Everything, because things converge, so it gives an apparent drop.
We're not talking about drop. We're not talking about elevations. We are only talking about horizontal angles. So what we call refraction, what you call optical drop, doesn't know that. So okay, if you're right about this convergence causing a problem with azimuth angles, then if you measure the angles in a full circle around yourself, they're going to add to a different value than 360 degrees. And that's not the case. We're talking about looking around our 360 degrees, and in the case of one of the survey stations, looking at 7 locations in that circle that around us at 360 degrees.
Do they? And then add up together.
All those 7 azimuth readings add up to exactly 360.
Oh, but you literally just said they don't ever converge to each other, so they have to take them and put the most plausible.
No.
That was your actual argument.
No, you're getting the wrong part of the argument. Okay, there's 2 things that go on. One is that they go and set up their surveying, their theodolite, at one location and measure the full look around them, in the entire 360 around them, and look at their they might have, in the case I showed you, there were 7 targets. And they measured the angular, hang on, here's my finger. They measured the angular separation between the 7 of those in their full 360 degree circle. Right? They move to a different location and they do the same thing, including looking back at that first station. They go all the way around and do those. Every single location, they measure 360 degrees and split it up to where their targets are. They take those individual angles and try and see whether they converge at another point. And because of margins of error, they're a little bit off. And so
margins of error.
That's right.
Where does the margins of error come?
From the measurements, because there is no such thing as a perfect measurement.
Because it's optical, correct?
No, because there is no such thing as a perfect measurement. It doesn't matter whether it's optical or not. It doesn't matter how you're taking a measurement. There is no such thing as a perfect measurement. Optical instruments are really great, but similarly, the measuring rods and the steel measuring tapes they use to measure the ground distances also have a margin of error in them. And so,
they used, like I said, you said they used measuring rods to do those horizontal datums, correct?
Not horizontal datums. No, they use those measuring rods to measure horizontal distances across the ground.
Great. And do those horizontal measuring rods give different angular sizes at different distances?
Why does they weren't observing them from a distance? They're passing them, they're leapfrogging them end over end and measuring how many times they had to put the rods end over end, like, you know, one after the other, to get from one location to another. What's optical
Right.
about that?
It's a distance from the theodolite, correct?
The distance from one survey point to the next was measured. Sometimes they use these measuring rods. Sometimes they use steel measuring tapes.
They use chains as well.
Well, not chains. Chains aren't that accurate. They use steel measuring tapes.
In India, I know they use chains.
Yeah, I know. But that's one way of doing it. They have an inherent.
I'm sorry to disappoint you, but I've
margin
been
of error.
debating this
Steel
subject
measuring.
for
Steel
years.
measuring tapes have a different margin of error. It was before the invention of an alloy called Invar. I think that was in the earliest 20th century. That's a particular alloy that has very, very low thermal expansion coefficient. But they knew how much these things shrunk and expanded in temperatures, so they knew how long they were. But there is still a margin of error in their measurements, in all measurements. And similarly, there was a margin of error in their measurements of angles. You can't be perfect. You cannot measure anything perfectly. And that's where the statistical process of least squares was used to not to find the exact answer, but to find an answer that gave the least amount of error across the whole network. And when they did that, these estimates of distances over 450 kilometers matched the actual on-the-ground distances. So that kind of shows that how valid this technique is.
Great. So they measured arc distances that matched the horizontal, correct?
No, they measured distances and angles. Sorry, they measured angles and then assumed spherical trigonometry. Yeah, and why are you waving your hands around?
That's an angle. Two straight lines forming at a vertex. That's an angle. So where's
two
the
straight lines across a surface?
Great. So across the horizontal datum.
Across a surface. There is no assumption. Datum. There is no horizontal datum is a planar surveying.
That was planar surveying.
Geodetic
surveying.
It was
surveying. Surveying comes after planar surveying.
No, you're actually okay. Let me tell you why. We often hear the argument, "Oh, planar surveys do small areas, you know, constructing buildings, roads, smaller things, and geodetic surveys do big things beyond a certain area." But in terms of the hierarchy of surveying, it's the other way around. Geodetic surveying is completely open to not making any assumptions about things. And planar surveying is a small subset of that, where they go, we can make some assumptions that make things easier because we're in a small area.
That's false. That's false. No, geodetic survey is specifically dealing with the assumption consideration of an ellipsoid.
No. It depends. It depends what sort of geodetic surveying you're doing. Like I've said in the start of my presentation, we have so much evidence of the shape of the Earth that these days some surveying can be done with that assumption already made. But there is nothing stopping you going out without that assumption and making measurements of without assuming anything about the shape of the Earth. You can make those measurements and provide evidence that it's spherical based on the angles that you measure. But like I said, we know so well the shape of the Earth. Current spheroid models are arguing about centimeters of radius or fractions of centimeters of radius. You know, when we're not arguing, is it spherical or not in science? We know this. And so you can do
Science is not shape. Science is not shape. Science is not shape-based, but we'll get to that's another. Okay, I just want to say, Tony Whitcomb, £5 super chat. Thank you very much. He says, Andrew, does water flow on a sloped surface or curved surface? If you answer yes, your presentation is bunk. If a no answer, explain why.
Well, the difficult thing about how that's presented is that, I'll give a more scientific answer. Water flows towards the place of lowest gravitational geopotential. So if there's a location that it's on and the surface leads down to a place that has lower gravitational potential, then it'll flow to it.
So
whether it's flowing on curved, I didn't. So what was was curved surface or what was the other one? On a slope.
Yeah, slope or curved.
Well, you need to tell me whether one part of that slope or curve has a higher gravitational geopotential or whatever the word is, and whether another location has a lower one.
So would you say then water can flow uphill?
So if you define uphill as being higher gravitational potential, then no, unless you're providing some extra force to push it uphill like a pump. But naturally, everything wants to flow downhill to the lower gravitational potential location.
Cool. So if you are on a different tangent plane to me, a different zenith, every tangent from my feet is away from me, correct? So if water's flowing down away from me and you're at a different tangent, it's supposed to be flowing down from you as well. But
no. So again, you need to tell me whether your local horizontal plane is on the same gravitational potential as my local horizontal plane.
okay, let's do your spheroid argument. At the equator, you've got the bulge, the equatorial bulge.
Okay. Again, that's another red herring. The amount of bulge is pretty small, and if you're going to say, well, hang on a second. If you're going to say it. Maybe this is not what you're going to say, but maybe I'm taking a guess here. If you're going to say that, then shouldn't water flow from the equator to the poles because the poles are, yeah, okay. Well,
and yet it flows up then to the equator, because the equator's got a bulge and it has more water.
Yeah, that's fine.
It's got a 21 kilometer bulge.
Okay. But that's where the idea of the gravitational potential of a location is not just simply the distance from the center of the Earth. Because of, wait for it, rotation.
What rotation? We're not even talking about rotation. You literally just said it's got to be the gravitational potential, which anyway is not a force because there's no such thing as a gravity as a force. The point is, you think your argument is then stating water can flow uphill.
No, I'm not. Again, the way I'm defining this, I'm being careful about this, it flows from higher gravitational potential to lower gravitational potential. The gravitational potential at the equator, despite the bulge at sea level at the equator, the gravitational potential is the same as the gravitational potential at the poles, despite the fact that...
That's false. Then you are going against your Eötvös effect now as well, because it's supposed to be further away from the mass, from the center of mass, so therefore less gravitational force.
Let's think. Oh, sorry, less gravitational. You're right. Sorry, less gravitational. Sorry, small difference there. No, I'm trying to balance up various different things, and I can't talk about this necessarily straight off the top of my head. Sorry, I got to say I don't have the concept at the front of mind to be able to talk about. I mean, the bulge at the, like I do say, the bulge at the equator, it's a bit of a red herring. It's a relatively small amount over a vast distance, and so bringing up the fact that the Earth is not quite spherical. Let's think about this. Sorry, look, I can't put numbers to it, but the fact that the Earth is not quite spherical doesn't suddenly make the water defining as flowing uphill to the equator.
Okay, that's also another question I wanted to ask you though, based on your triangles.
Yep.
Wouldn't they show a much greater arc if they were measuring down to, like in Africa? Remember you showed South Africa where they took it from the south to the north. Did they in the northern part of South Africa show a greater arc measurement?
Yes, absolutely, they did. I didn't go into it because, although I read up on it. So, for my later arguments where I was talking about the assumption of spherical, the assumption of curve matching the on the ground curve, they actually did consider the difference in curve between the slightly northern parts of their survey and the slightly southern parts of their survey, because the Earth's radius is slightly different at those. They did actually consider that in some of the calculations.
So they changed the considerations then. That's why they gave different type of parameters for it because of
ever so slightly. Now, importantly, hang on. Because they were measuring across the 39th parallel, right? If they were going straight across the 39th parallel, then they would have considered the same radius value the whole way across. But as they went across the country, they went up and down a little bit. And so they made different considerations of the assumed radius in some of those calculations based on if they were a little bit further south or a little bit further north. They also made a difference between whether the measurements were going horizontally, so it's based on the equatorial radius, or whether some of their calculations were going north-south based on the polar radius. They did actually did use the different radius values depending on which direction they were going in. Very, very small differences because they were going across the latitude line, so the radius didn't vary very much. Now, but as for talking about north-south surveying, like you said, up and down South Africa, Southern Africa, way back in those earlier surveying that I presented early on, that Picard one in 1670, that was a north-south done in around Paris. Now they didn't suspect that the Earth was spheroidal at that point. They did a north-south measurement of 1 degree of arc and came up with a certain value of the circumference. A little bit later on, that Paris meridian was extended all the way from the top of France right down to the Mediterranean to the bottom of France by one of the Cassinis. It's a name you'll hear from astronomy. And based on their measurements there, they actually thought the Earth might have been a prolate spheroid, that is longer at the poles, longer like, I don't know, a lemon, rather than flat. Yeah? Sorry?
Or sort of elongated, almost like pear-shaped.
Not pear-shaped, but elongated towards the poles. That's what but, the measurements are very fine. And, but, over a couple of thousand kilometers, they said, we think it's this. And that's where the French then sent surveying expeditions to the equator in South America and to the Arctic Circle in Finland, doing much more accurate measurements than that first one. And then they came up with different radius value. They got a different radius values at the equator than the ones that they measured at the Arctic Circle. And since then, all this surveying done to enough precision has shown that the Earth is actually bulging outwards, not bulging upwards. So there is a difference in radius shown. In fact, one of the other surveys done by the United States at around about the same time as the one I did was called the oblique arc, which was a oblique meaning at an angle. So it was an angled survey going along the east coast of the US. And so that in that one survey, they were able to measure. They were going east and west, and they were going north and south. And so they're getting lots of different measurements of the radius values as they changed east-west and as they changed north and south. And it was due to the summation of the data from that survey, the transcontinental triangulation. There was another north-south done through Texas, I think, at the time. And with all those huge surveys done, north-south, east-west, and diagonally, the US Geodetic Survey decided that they would choose the Clark spheroid as what they would use for their mapping, as opposed to the Bessel spheroid, which was an also common one at the time. And the difference between those two spheroids is very small. It's only, for the semi-major axis, it's only a couple hundred meters difference. And they came up to the conclusion, well, we find this one's a little bit closer to what we measure here in the US. We're going to use this one and not use the other one.
Great. So again, after all that, they considered it to be a sphere. So they believed it to be a sphere after measuring it on what? A horizontal plane.
No, again, in the start of my presentation, I gave you a history of how we've become to understand the
I've read through that whole 900 whatever thing before. I've actually been debating this for many years.
Yeah, not a problem. But this was the development of understanding of our shape of the shape of the Earth. And by the time we get to the 1800s, we're pretty confident about it is, and we're just refining it and refining it and refining it. Now, you still say that they had an assumption of sphericity. Well, they did in some of their calculations. They assumed it and found that it matched what the ground looked like. So basically, you're predicting what the ground looks like. You measure it, and you go, well, it matches our predictions. Therefore, our predictions are probably right. But
horizontal. No
one said horizontal. You're saying that.
You literally brought up in your presentation the horizontal.
What did I bring up about the horizontal?
It was close to the end of it. You're going to have the paper showing horizontal. It said in its title, the horizontal.
I'm not sure which bit you're referring to. I'm sorry.
It was close to the end of your presentation. Maybe you can bring it up again.
Okay. I don't know which bit you're talking about being horizontal. So I'm just looking back at my horizontal control. Was that it?
There we go. Horizontal control.
Right now. So hang on. Let's just just give me a second. I will just. How do we? Oh, brilliant. So share screen. Just a second.
So I just want to ask, do you know what the horizontal
That
control
one
means?
is that the one you mean? Horizontal control.
There we go. Yeah. So do you know
Okay.
what that horizontal control is?
Yes, I do. And if you don't know it, then that's fine. I'll explain it to you. Horizontal control is about measuring the distance across the surface that places are located. It's known as horizontal. Now, that is not saying that it is a flat plane. It is saying what is the horizontal distance across the surface of the Earth, whatever the shape of that Earth might be. What is the horizontal distance, as opposed to what is the vertical distance, like what is the height of this location. So when you look at a normal map, you talk about two cities being separated by 300 kilometers, you're talking about the horizontal distance across the surface. You don't care that one's up in the mountains and one's down in the valleys. You're just talking about the horizontal. And again, I say horizontal does not mean it's planar. The horizontal distance between those two, as opposed to the vertical distance. So it's called, in geodetic surveying, there's horizontal control and there is vertical control. And so what I was talking about through this whole thing about surveying is just what's called horizontal control. They're finding, controlling, measuring how far things are apart horizontally. Now, in the transcontinental triangulation, they actually did some vertical surveying as well, with differential leveling, astronomical things as well.
Angle. With elevation angle.
Yes, but what I've presented, what I've presented actually has no does not include and does not need to include any of their vertical measurements at all. It is only the horizontal. Actually, there were two, and I pulled it out of the presentation because it was getting a bit long. There were two places. I'll take that back.
Could you be able to define for me what horizontal is to you, though? Because as far as we know, horizontal is just horizontal. There's no curves. It's no slopes.
You're using the word in the normal everyday, usage of the word. Oh, it's horizontal. It's flat. It's flat. It's horizontal. Nothing.
Horizontal means.
Because in our normal small scale experience, that's what we talk about. Horizontal control in surveying has a definition, and it does not define it as being a flat plane. It means the horizontal distance across a surface between locations.
From A to B. So if it's, let's say, like they did, point 1 to point B was 17 kilometers, for instance. That's a horizontal distance of 17 kilometers that they measure.
That's a horizontal distance across the surface of whatever object it is on. It doesn't matter what shape the object is. It is the horizontal distance that you have to travel across the surface, ignoring any vertical things. It's the horizontal distance, yes.
Great. So flat then.
No, I didn't say flat.
Because 17 kilometers apart, and they measured it from point A to B on a horizontal plane.
No, they measured it across the surface.
Do they have two different horizontal planes then?
They don't care. They don't make any assumption about the horizontal plane of one
horizontal
being.
Making a claim. Horizontal isn't making any claim. You do know why they use a horizontal datum in the first place, right?
No. Horizontal datum is a planar surveying where you make the assumption that everything around you is planar.
When you set up your theodolite, you're creating a horizontal datum. That's how you actually calibrate it. You set it up and calibrate it.
No. You don't. No, a horizontal datum is different from your local horizontal direction. So you have your vertical, and everything is derived from vertical. You have the vertical, and you find the direction that's orthogonal to that, like perpendicular to that, and that no, not a plane. That is the direction at your point that is considered horizontal. The direction, right? So all around me, that direction. But I'm not saying that
horizontal. Then it's an infinite horizontal from your zenith.
You're making a difference. You're making a difference between a direction, being pointing in a direction, and everything extending in that direction, right? Your local horizontal is not a plane. It's just a local horizontal direction.
That horizontal, what's the name that you just put up there? Is based on a horizontal plane. That horizontal distance is the horizontal plane.
No?
Yes, it is.
Again, you're talking about the horizontal control.
Horizontal control is a horizontal distance over a single horizontal plane.
No, over a
Literally
surface.
A
Over a
surface,
surface.
the same surface, correct?
Yeah, but there's no assumption about what shape that surface is.
Let's put it this way. 20 kilometers A to B, horizontal distance on the same surface, aka the same horizontal plane,
No,
aka
you've just jumped to an assumption.
no curve. There's no
You've just
assumption
jumped
there.
to, you've
It's
just to
simple.
assumption.
That's what it is. That's why I
Yeah.
was happy you brought that argument up, because you just literally, when they did that, you know, that triangulation link they used when you said they have the arc measurements, that's because they measured optical, not physical.
The optical
Yeah.
thing, red herring. Who cares whether they measure optical or not? You haven't shown
Who cares? Yeah,
any
because
reason
it
why.
debunks your argument.
You haven't shown any reason why optically measuring the separation between 2 points as on at your local station doesn't match what the actual physical real world angular separation is from those things. What's it matter that you measure it optically? Like the problem is you say that optical measurements are somehow wrong. Well, then you're throwing away all of surveying. You're saying that it doesn't matter what you do in surveying, you're not right.
The surveying is based from optical measurements. In other words, you take
not necessarily
optical perspective, and you are, because of your belief in a globe, you're calling it physical curve.
No,
this whole presentation is you literally providing us evidence it's flat.
Well, the problem is you're trying to say that optical measurements are not valid. Now, in planar surveying, you do the thing where you know about closing.
That's false. When did I ever say optical measurements are not valid?
You bring up optical measurements as if because they sighted these things through a telescope and measured the angle on a base plate of their theodolite, that there's something wrong about it. That what they're actually measuring as an angle is not the actual physical angle that's separating these two things. How is that not the case? How is that
optical angle measurement based on a horizontal plane? Those corrections that you are calling spherical axis is because of optics.
No.
It's not a physical drop. That horizontal distance of, let's say, 400 kilometers across on the same horizontal plane means it's flat.
No. Where are they saying? Where in the stuff that I presented? Sorry, I just wasn't concentrating for a second. Where in the surveying that was done in the transcontinental triangulation was there an assumption of a horizontal plane that things were separated by? There wasn't.
You just literally brought it up. Horizontal distance.
Horizontal control. Horizontal distance across a surface, right? Without any assumption.
Surface A to surface B. All those linked triangles, let's say 400 kilometers, linked from A to B, are they based on the same horizontal distance?
Well, they measure the angles and therefore deduce the horizontal distances, but horizontal distances across a surface. And my third point was that when they calculate those horizontal distances across a surface, when they make the assumption of curvature, their horizontal distances match with what they actually measure 450 kilometers away. If they made those calculations based on a planar surface, they wouldn't come up with the same answer.
Again, that's an optical measurement which they stitched together.
You're bouncing around. You're telling me it's horizontal.
It is horizontal.
It's a horizontal plane. I'm telling you it's not a horizontal plane. And then you're going, oh, well, it's optical measurements. And I'm saying, well, what's wrong with optical measurements? And then you're jumping back to it's a horizontal plane. What is your objection to optical measurements? And again, I say, if you stand...
objection to it. I'm happy they use optical measurements, because the mere fact they use optical measurements means they are taking optical measurements, and you got perspective, and you see optical phenomena, and you're taking that, what you see, and measure in optical reality and call it physical.
So the question is, if I stand somewhere and look in one direction at something and then move around and look in the other direction at something, that angle that I'm measuring here at my body between one and the other, I get a certain number. Okay, you got a margin of error, that's fine. I get a certain number. How is that certain number not the actual physical, real world, genuine, in reality, angular separation between those two things. What does it being optical change about that angle? Does it make it smaller? Does it make it bigger? Does it just make it less accurate? What does optical do? As opposed to physically taking maybe a long straight ruler out that way and a long straight ruler out that way, so that I know I'm physically measuring the separation and then measure the angle between it. What difference does that make between whether I do that or whether I do it with my eye? What difference does it make to the angle? Does it make it bigger? Does it make it smaller? Does it make it less accurate? What is your claim?
The claim is you use a theolodite. You know that horizontal line on the theolodite, that's the horizontal datum you set when you set up a theolodite.
We're not talking about horizontal.
Have you ever set up a theolodite before?
Irrelevant.
I'm guessing not. Okay. You know when you have to set up a theolodite, it has to be perfectly horizontal to the vertical. That's how you calibrate it. You already set in your considerations and everything based, because you need the corrections to be horizontal. That datum means reference.
No, datum's different. A datum is different.
A theolodite in different locations, measuring a horizontal baseline. That's why I love that the word, yes, horizontal.
No, you're not measuring a baseline, you're measuring an angle.
Your whole argument in your first argument was based on baselines.
No, you measure angles between everything, and then you scale the entire thing with one baseline, and that scales the whole size of everything. Because angles don't give you sizes, they just give you separations. And then you then based on that one little measured baseline of like 8 kilometers, that gives you a scale for the entire thing. So
scale based on the baseline of a horizontal plane.
You know, the baseline is just as a horizontal measurement.
Yeah.
I don't know what you're getting at here.
So remember when you brought up that thing and they didn't measure from that point to that point, but they worked it out and they were a centimeter out. How far was that distance again?
450 kilometers was the separation that they did the prediction across. The actual line that they were trying to measure between those 2 points was, I don't know, 3 or 4 kilometers, and they were 1 centimeter out.
Great. And they were based on a horizontal datum that they used for all their measurements, correct?
No, they're not. They based it on a curving datum.
So do they use a curved baseline? Is that what you're telling me?
No, they didn't use a curved baseline. They used one measured baseline.
Curved distance baseline. Thank you.
Don't bring up the curved baseline. That is the argument that goes with celestial navigation and elevation angles. We're not talking about curved baselines. We are talking about measured baselines.
Yes, measured baselines on a horizontal. The horizontal is the measured baseline, which is not curved.
Measured baselines along a surface.
So the surface is horizontal.
The surface is not assumed to be flat.
No one said anything about assuming flat. We're saying horizontal. Horizontal means flat, not curved.
No, it doesn't.
Okay, bring up the definition of horizontal quickly, please.
We're not going to play the definition game. We know what we're talking about. Don't
I've got the definition to back me up. Do you have the definition to back you up?
What I'm saying is that in the survey, they measure a distance across the surface of the Earth. They measure angles between locations. They do calculations based on now wait for it. They do calculations, the trigonometry based on an assumption of a radius of curvature, and find that their predictions match hundreds of kilometers away. Match their predictions of another measured. And you're bringing up optical again. You still haven't quantified or qualified what makes an optical measurement of horizontal angles inaccurate.
Okay, your whole statement now just literally validated my point. Them making this measurement, which is optical, and they claiming it to be physically curved, is saying my optical measurement means it's physical. Just like when I took that rhetoric video where I took the capsule, I took the inferior mirage away, where they're claiming now, oh, I took my curve away. This is exactly what you guys are doing with this. You're making an optical measurement and calling it physical curve, simply hijacking perspective. And you just literally validated that with this whole presentation.
So, Flatzoid, you still haven't told me what is it about an optical measurement of an angular separation that will make it different from a physical measure of that angular separation. I ask you, is the optical measurement,
Okay.
is it larger? Does it make it smaller? Does it make it just less accurate?
I can answer that. Do parallel lines in perspective really converge?
No,
Or do they
that's irrelevant. I'm asking about.
No. It's
I
just
am asking.
perspective.
I am
Optically,
asking.
do the parallel lines appear to converge, or do they actually converge?
But what difference is this going to make to a measurement of angular separation?
Exactly what it's going to do. It's
What's it going to do?
optical.
What's it going to do?
When you're looking through your theodolite, sorry, I'll keep pronouncing it wrong. Theodolite.
Don't worry, I'm used to it coming out wrong.
Optically, you are seeing parallel lines converge, correct?
I'm not looking at parallel lines. I'm looking at one target.
Through theodolite, you do not see parallel lines converge.
No, but we're not doing this in this survey. We are looking at one location. We are turning around and looking at another location and measuring the angle between them.
Exactly, based on optical measurement.
Yeah, and what does optical do to that?
Just what I'm saying. You're looking out into the distance. Parallel lines are appearing to converge. They don't physically converge. So that appearance of convergence, which you call curve or spherical axis, is only optical, not physical.
You're still not answering my question. We're not talking about standing in between train tracks and watching them come together. We are talking about looking in one direction, looking in another direction, and working out the separation between them, right?
When you're looking in one direction, you have an optical measurement. Then you're looking in another direction with another optical measurement.
You're not actually measuring it optically. You're just using the optics to point in a direction, and then using the optics to point in another direction. And down here on your base plate of your theodolite, you're looking at how far it says it's moved around between the two. So what does the optics? I'm still getting the point. You won't answer. Is what does the optical measurement? How does that affect the measurement of that angle? Like, they are physically in the world. There are two objects way off in the distance at different locations, and if you trace virtual lines back to you, to that vertex, there's an angular separation between them. So there is a physical angle that they are actually perfectly separated, right? And so you take an instrument and measure the separation between one and the other, and you get an angle. How is the one that you've measured using your optical instrument by turning it from one side to the other, how is that different from physically running a tape out that way and a tape out that way? So you're physically measuring the angles to those. How is that different from optically pointing a telescope of a theodolite that way and that way? What sort of difference are you going to get in the angle?
Were all those points at the same distances from each other?
Doesn't matter.
It does matter. Distance changes how you perceive things.
Okay, so hypothetically, those two targets that I'm looking at are both 5 kilometers away.
Okay, so point A and point B, let's say both 5 kilometers away.
Yep.
Okay, now you're looking at it at roughly the same time. So the sun is in the sky roughly the same time. The light is dependent on different angles, correct? You got different.
The lighting has nothing to do with it. The lighting has nothing to do with it.
Different variations. Refraction. Remember, that's even in your presentation. You said they don't want to take refraction, otherwise it's going to complicate.
No, hang on a second. First thing you said, the sun was in the sky. Blah blah blah. Doesn't matter. How those two targets, how you find those two targets is irrelevant. During the day, they would use a heliotrope. They would actually use a mirror signaling mirror. If they're far enough away that it's hard to see. At night, you can use a signaling lamp. During the day, you can, if it's close enough, you can see it. It doesn't matter how you see the target. That doesn't matter. Now, second thing.
How far were those distances?
5 kilometers, let's say. Just, I don't care.
And how high were they? What is the elevation with the theodolite?
Well, so elevation above sea level, or do you want the angular elevation?
Elevation angle, correct, to those mirrors.
Some of them would be below the observing site. Some would be above. Some would be at the same height. Doesn't matter.
But I'm asking because now some of them would be, let's say, 10 kilometers away, and they would see the mirror, correct?
Yeah.
And a theodolite is usually what, maybe a meter and a half in height, correct?
Right. What are you getting at?
Why are you claiming you're supposed to see that mirror?
I'm not sure what you're getting at. That you're okay.
Where's
It'd be
the
great
curve?
these days. We could communicate with phones or whatever. In those days,
Where's the
distances along the way, they would use a signaling mirror, and so you'd see this little bright speck of light in the distance, and you would aim at that. I mean, that's irrelevant. You could do this. You could do this measurements over short distances, a couple of kilometers, where you have no problem seeing what.
So you can see a light 10 kilometers away from standing a meter above the ground.
You're not a minute. No, you need to have line of sight to your target, obviously, and that's why I showed
10
you.
kilometers away.
Sorry?
Some of those measurements you showed were 16, 18 kilometers away, correct?
Some of them were up to 185 kilometers away.
And you have line of sight.
Absolutely. Can you
So
not see
no
can
curve
you not
then.
see a mountaintop,
So
like
no
a
curve.
3,000 meter mountaintop from 185 kilometers from another 3,000 meter mountaintop, and there's only a valley in between?
So no curve then, no horizontal distance.
No, I didn't say that. I didn't say that. So there were some very long measurements over 100 up to almost 200 kilometers away. Absolutely,
Okay,
no problem.
Then let's take those ones that were on
hang on,
zero.
how far
Let's take
away?
those ones that are like on 0 degrees mean sea level, and they took a
Sorry.
measurement out 20 kilometers away, and it was.
Sorry, Flatzoid, I missed that. We were both talking. I missed what you said.
Oh, sorry. I'm saying, okay, then let's take one that where they were 1 meter above sea level,
Right.
and they measured something 20 kilometers away or 25 kilometers. It was line of sight to that 25 kilometer.
Yep.
Where's the curve?
Well, what if that 25 kilometers was up on the top of a 4,000 meter mountain?
Again, 1 meter above sea level.
I don't care. It doesn't matter if the thing's 4,000 meters high. You'll still be able to see it. I don't know. Look,
Do you know what
we're making up numbers.
means? Do you know what above sea level means? MSL, mean sea level.
Well, yeah, obviously, yes. But
So 1 meter means you 1 meter. You're not on a 3,000 meter.
no, but your target is 3,000 meters up.
Oh, so you're measuring a straight line angle, line of sight to the target.
You're pointing at one target. Doesn't matter if it's above you or below it. As long as you can see it, you're pointing at one target. You turn around and you point at another target. You measure how much you move between one and the other. Arguing about elevations, arguing about altitudes, curves, whether you can see the thing or not is irrelevant. You can't do these observations if you can't see your two targets.
Thank you. That's my whole argument. You can't do it if you can't see the what sense. And those measurements go totally against your radius of what you should see on your Earth.
Hang on, which measurements? I'm talking about being on
Your-
top of one hilltop and seeing another hilltop 10
They weren't
kilometers
just
away.
They weren't just on hilltops. They were on lower grounds as well. There's a lot of measurements where they were literally a meter above sea level.
They were very rarely 1 meter above sea level. There's very few locations between New Jersey and California that are only 1 meter above sea level. And as I showed in my presentation, they erected 80-meter high target towers in lower country where on the ground they didn't have line of sight. So
Those photos you were showing, there was a few of them where they literally had to break out on the ground from the road so they can see their target.
No. Yeah, hang on. Let me get some of these pictures back
Some of
up.
those photos were showing them literally on flat ground.
Hang on a moment. Let me bring up. I'm just going to bring up pictures. No. So, are you talking about that picture?
One of them, yeah, that.
Right. So that was the clearing of the ground, so they could do the baseline measurement. That was not to do the measurements of angles between locations. That was just so they could run their measuring rods end over end between one location and the next. That's not what we're talking about.
And that you saw it was going like this, correct? It's like
sorry, I wasn't watching your screen, but you're probably saying it's going up and down over mountains.
Would that change what distances you could say when they put
Yes,
end to end?
and they accounted for those angular changes and things like that. I mean, these days, if you were doing what's it called, differential leveling, you would measure level out and then you'd step down a bit. You'd level out, step down a bit.
Slope angles.
Right? They would do things like that, and so they would account for the fact that in this picture you're going across a gully. They would account for the extra distance for doing that. And
Slope
they would sort of,
angle. So they literally measure the physical surface and base it on a horizontal datum.
no, they measured the physical surface and then calculated for all these undulations what the actual direct distance between those two locations would
Slope
be.
angles, yeah. Slope
No, not
angles.
slope angles. Slope angles
That's
have
a
nothing.
slope angle. If you had to put
Yeah.
a theodolite where they are now,
Yeah.
it has
So,
an infinite datum,
so
horizontal
now,
datum.
now,
The slope
now you're
angle
trying to-
is even there. Is their
now you're trying to
correction.
bring into disrepute or bring into doubt the measurement of the on the ground distances. This one shows that they went up and down hills between these two locations to measure, let's say, 5 kilometers. They would, of course, measure the up and down slopes and realize how much extra distance that was adding to it. They would factor that out and work out what the actual straight line distance is. Now, importantly, since about the 1950s, we've had EDM, electronic distance measuring equipment, and that's one of the main components. Okay, you're nodding your head. You've heard of this.
Like LiDAR.
Sorry?
They got like LiDAR, like they use LiDAR today as well.
Yes. So you would use radio waves, microwaves, things like that. That came about in the 50s and 60s. Forget about it's not an angle. No, it's just distance.
It's all based on slope angles from a horizontal datum. That's how it works. You can say no all you want. That's what it is. I don't know how much more I can explain it to you.
Well, when you're measuring the direct distance between two places using, say, radio-based electronic distance measuring equipment, there's no you're measuring a direct straight line.
Yeah, let's say the one is on the bottom of a hill like this,
Yeah,
and the other one's there. The receiver and the other one, they're pointing at a slope to each other. That's a slope angle.
Yep, sure.
Yeah.
Yeah, but if you then want to work out the direct, if you want to work out the direct horizontal distance, you just do the trigonometry and work out what if it wasn't a slope angle, what would it be? What would the distance be? And you just do the trigonometry. You just do the equation.
On straight lines.
Yeah, straight lines don't mean that the world is straight.
Oh, that's what it means. You have straight lined angles measuring slope angles and then calling the axis spherical.
That's kind of a nonsense statement.
That's what statistical zenith angles mean. It's the belief that angle measurement slope axis is curving away. That's the belief of it. It's not physically curving away. It's your belief that it's curving away. So you calculate it as a spherical axis. Not that it is a spherical axis. Like I said, I've been debating this for years with surveyors, so it's nothing new to me, mate.
Right. So we're going to go back to this one, right? And we're looking at I probably shouldn't have got that one. I probably should have got one of the other ones. But these are the triangles in the Salt Lake base net. And over on the left, actually, I'll hang on. Right, actually, let's go. Hang on. Sorry, I'm just going to move to the screen that I wanted. Oh, that'll do. We'll go with that one.
I just have to state quickly, the power is going off at 11, so I think we're only going to have like 10 minutes still.
So that's 10 or 15 minutes away. Okay,
yeah.
No problem. So here we have what I in the red boxes, the sum of the observed angles for 5 of the triangles in the Salt Lake base net, and they all have excess angles. How do you explain that? And don't say it's perspective, because you haven't told me how perspective. I'm just going to stop sharing that. You haven't told me how perspective affects the angle that you actually measure. You just
go back to the screen share quickly.
Just give me a second. Hang on. What am I going to do here?
Hey, Moomin Rider.
Oops, that's not what I want. Sorry, just hitting the wrong buttons. Give me a second.
I just want to say, Moomin Rider, I got your email. I will respond to you. That's actually quite idiotic what that guy was saying on that video.
Okay, there we go.
Okay, I see the one is 46 kilometers. And it's giving a what? 98? Yep. I can't really see properly.
Okay, 46. So so it's triangle 19 on the left side of the screen. It says number 19. Yeah. Is that one you're talking about?
Yeah, triangle 19.
Yep. So distances of 46, 185, and 142 kilometers. Those are the side lengths that were calculated. But so the first thing they did, they didn't calculate. They didn't start with the side lengths. This is just the results. They started with the observed angles, which is over here on the left, which I've then got the summary of the excess in the red box.
Great. And how did they get that summary of the excess?
They measured the angles from all sorts of different surveying stations, and then they took the 3 angles that formed this particular triangle between these 3 locations and then added them up. And they added them up, and it got to more than 180 degrees.
But are they different distances?
We're not.
All three. No, but I'm saying all three. Pilot Peak, what's it?
Promontory and Ogden Peak. Hang on, we'll
they're
make it a
all
bit.
different distances, correct?
No. Pilot Peak, Promontory, and Ogden Peak. They are 3 locations where they
But
did
at different
surveying from.
distances. At different distances.
They are 3 different locations. They're the points that make up your triangle. They're 3 locations, and as it happens, after doing their calculations, over on the right-hand side, this is how far they calculated those 3 were apart.
Right, so different distances then. Over what did you say? A horizontal distance, surface distance.
No, the angles here are just the angles at each of those 3 locations at horizontal angles measured locally.
Great. So to break it down again, they measured a triangle from a horizontal datum.
No, they didn't have a horizontal datum.
They had slope angles to give their
They didn't use slope angles.
A theodolite uses slope angles. That's how a theodolite operates.
No, a theodolite has 2. It has an altitude measurement and an azimuth measurement, and in this is just the azimuth. This is not the slope angle.
So the azimuth would be below the horizontal datum.
There's no horizontal datum. The azimuth is the horizontal angle at their location.
What's that line what's that horizontal line that's on the theodolite, on the lens? There's a horizontal line there.
That's irrelevant. No. In this case, you're just using a target, so you might have a crosshairs.
That's what I'm saying. That's a crosshair. Now, when they use a measuring rod, because they probably use measuring rods, correct?
They didn't use measuring rods in these observations. These are just angles.
Yeah,
sorry,
because it's far distances. Because these are very far distances. So
okay,
they measured angles. How do they measure the angles if they didn't have a measuring rod?
No, we don't measure angles with a rod. You measure angles with an angle measuring device, and these distances, these were not measured distance, these were the calculated distances based on these angles.
They used the theodolite and they looked out in the distance. How did they get the angle measurements using the theodolite?
When we've talked about that, they'd point from Pilot Peak, they would point to Promontory, and they would point to Ogden Peak and find that there was 6 degrees and 8 minutes of angular separation between them from where they currently
those
stand.
Angular measurements are based on that horizontal datum inside.
No, it's based on their local horizontal plane.
Great. So horizontal planes, then the same thing you've been denying this whole.
No, debate. I haven't been. I've been denying that there's that there is any assumption that the horizontal plane at these 3 locations are the same plane. There is not. In fact, it's quite the opposite. It is not assumed in some parts of this.
They're different elevations, correct? They're different elevations.
It doesn't matter whether these 3 points are at different elevations.
Yes,
It's irrelevant. No, it's irrelevant. We're only measuring the horizontal angle between them.
If you have a okay, so the guy at section 19 or whatever, the station 19 is pointing. He's standing exactly the same position, correct?
No, okay. These are not the okay. They stand at Pilot Peak and they look at Promontory and Ogden and find that there's 6 degrees. They stand at Promontory, they look at Pilot and Ogden and see 154 degrees. So this is not
the. They move to a new location.
So these are the observations from 3 different locations of within this triple. These are the observations from one location, the angular separation to the other 2 locations in the triple.
That's my point. Every single one of them have different elevations.
Elevations is irrelevant. How does it? They may
irrelevant.
Hypothetically, they might be at the same elevation. It doesn't matter. We're only talking horizontal angles, azimuth angles.
Have different elevations.
Sure, but it's irrelevant because you're only looking at the horizontal angle, but the azimuth angle between them. So it doesn't matter if one's high up, one's low down.
Oh yes, that is. Azimuth angle definitely changes due to your elevation.
No, it doesn't.
That's your globe claim. Why do you think you have different latitudes?
That's not making any sense to me.
You have different.
No. Hang on. You're talking about elevation angles to a celestial object being a way of determining your latitude.
No, I'm not talking about celestial object at all. Okay. We're talking about to the object, the mountains.
You just talked about elevations and latitude. There's in the triangulation survey there.
Sorry, I missed that. Elevation. That theodolite. when you're
The
using
other
it, you're usually setting it up at an elevation. Doesn't matter where on earth, it has a certain elevation above sea level.
And what difference does that make?
If you are taking that elevation and you're going to look out and you're moving it to another location, you got a different elevation angle. So therefore,
We're not talking about elevation angles here. I wish I could give you a 3D demonstration, but if I've got, I don't know, look in front of you, look at two keys on your keyboard, and they've got a certain separation, horizontal separation, right? If you stand up higher, does that change that horizontal separation?
Angular, yes, it does, because things shit.
No, if you stand up directly on the spot, the horizontal difference between looking at one and looking at the other is exactly the same, no matter whether you stand up really high or down really low. If you're right down low to your pencil,
then why do they claim from the ISFs when they're up?
You're moving on to something else.
For instance, it looks this small. Is that now the same distance as when you when I'm now
the horizontal angle? I am only talking about the horizontal angle.
That's a horizontal angle.
If you think I'm going to demonstrate. I'm pointing. I know you can't see my hands properly, and I know we're running out of time. I'm pointing at the extremities of my computer in front of me. Now, if I stand up directly, the angular difference between those two locations, the horizontal angle, now it looks smaller. So it looks, if I look down at the slope angle, it's getting smaller. But if I'm just considering the horizontal angle, that doesn't change. So the fact that one survey station was higher than another survey station doesn't make any difference.
Change the distance? Does elevation change the distance from you to the observed object?
But the calculated distances of those triangles are adjusted down to sea level. They are only the horizontal.
What I'm asking, does the distance change because of elevation?
But the question I'm still getting to is, how does that change the horizontal angle?
No. Does the distance change with elevation?
Does the slope distance, the direct line distance, of course it does.
So it changes the angular size then. So therefore angle changes.
No, it doesn't.
You just said yes.
The horizontal component of the angle doesn't change. Now, there are elevation corrections that they did make for significant elevations across the Rockies for the survey. The difference that being a couple hundred meters higher here and there for a survey across 4,000 kilometers, the fact that some are a little bit higher and some are a little bit lower will make an extremely small difference. And in fact, in the survey, they made an analysis of how large those differences would be if they made elevation corrections to their angles. And they determined that, except for in the Rockies, in the west and the coastal ranges in California, through across the very, very flat parts and low parts of the plains of the states, and even through the eastern mountains of the states, they determined that the amount that an elevation correction to their angles would make would be smaller than the precision of their survey. So for most of the survey, they didn't do elevation corrections. But for some sections of the survey through the Rockies, they actually did take the elevation, like the heights above sea level of their stations, and calculated to bringing those stations down. And that is another... One more sentence. And that also contributed to the accuracy of their predictions. So by doing those altitude corrections, they made very small differences to the calculations of their distances across those long chains, and was still able, across the Rockies, across an area where it was 800 kilometers between two measured lines, and they had distances of 100 to 200 kilometers of their triangle distances, they still got, when they got to the next baseline, they still got to within about 20 centimeters predicted versus the actual measured. So again, they did all these corrections. There were some corrections that involved an assumption of a radius of curvature. There was an altitude correction. They assumed that the whole thing was an arc, and they still came out to within a handful of centimeters of a distance that was 800 kilometers away.
So I'm making my point then.
What's the point?
Optical measurements, and
you still haven't answered how an optical measurement of an angle is going to differ from a physical measurement of an angle.
Remember my trying to explain perspective and orthographic view.
That's all very nice to talk about it in general terms.
That is exactly
what is going to change? I've asked you this so many times. I physically measure an angle by physically putting a ruler out there and a ruler out, well, a rod out there and a rod out there, and physically touching those things and measuring that angle. I take the telescope of a theodolite or anything at all, and I do the same thing. I optically look at one, I optically look at the other, I measure the angle. How are those two measurements going to differ? Why does optically measuring it versus physically measuring it with, a physical straight rod going to make a difference to the angle?
It doesn't make a difference to the angle. The point
Well, there you go. You're trying to tell me that there's something wrong with optical.
No.
And you're not telling me why it's wrong.
What you're doing is taking the optical effects.
What
and
optical
calling
effect?
it spherical excess.
What optical effect? I contend that if you could run a straight line of 185 kilometers to Ogden and 80 kilometers to this one and another one across there, I contend that if you measure with a physical straight connection between them, you would get the same angles and you would still get more than 180 degrees. Measuring those angles optically from your local location at those 3 points is not going to make any difference other than difference of margins of errors and things like that. It's not going to make any difference to what angles you actually measure. You are still going to get excess angles. Measuring them optically versus measuring them physically does not make any difference. And you haven't provided any reason other than saying perspective.
How would you measure something physical 100 kilometers away?
With a very long and a very straight. Well, my contention is if you could. Now, they don't have to be 180 kilometers away. The only reason I chose those ones is because the margin of error of your measurements was smaller than the spherical excess. At those small triangles in Kent Island, the little margins of error in making those optical measurements was overshadowing the excess, and that's where the statistical averaging sorted that out. But over those big triangles, the excess is like if you could make a theodolite that was 100 times more precise and accurate than the ones they use, then you could use smaller triangles and you would still find the excess, and there wouldn't be any problems with that. So
that's what I'm saying.
When you measure the angle, sorry,
that's what I'm saying. The calculated excess you're giving is
measured excess. Measured excess.
Not because of physical curve, it's because you measured it optically. That's why.
But why does that give you excess? You haven't explained why that makes the angles bigger.
Because things don't physically converge in the distance. It only optically converges. So when you are pointing your theodolite to a point, you are physically pointing it somewhere, but that optical place you are pointing to doesn't actually mean it's
so it's not there. You're pointing your theodolite there, but you're telling me the actual object is over here. Is that what you're telling me?
You have things, especially at far distances, you have things like refraction.
No, refraction only happens vertically. We're only talking horizontal angles.
Refraction happens at 100 kilometers, whether you like it or not.
Yeah, but it happens vertically. We're not dealing with vertical angles. We're dealing with horizontal angles. Have you got some proof that refraction
horizontal angles, but your theodolite is on a vertical plane, just like it's on a horizontal plane.
You're just talking nonsense. There are vertical angles, there are horizontal angles, and we are only dealing with horizontal angles, and refraction doesn't affect that. Refraction only affects vertical angles.
Okay, we're going to have to end here. The power's about to go off. But like I was saying, it literally a theodolite. You might want to go and look how it's structured and how it works, and then you'll see elevation angle is always there. If they use a theodolite to take...
We are not considering the elevation angles. We are only considering the azimuth angles.
Anyway, you just
I know time's about to run out.
Yeah.
Let me just say a few things. I appreciate you having me on. It's taken a long time to organise this. I've done an awful lot of reading and spent an awful lot of time on it. And I do appreciate that it's only been the two of us talking here. We haven't talked over each other too much. We've been pretty civil about it. That's really great. I do appreciate that. I'll give my final thoughts is I presented things showing that spherical excess is empirically measured. And the best you can say is, well, you're measuring it optically and you haven't told me how optical makes those angle measurements wrong or different or, somehow puts extra angle in. So I'll leave it at that. I appreciate you having me on. Maybe some other time we can talk about other subjects. It's been good. Thank you.
It's been a nice guy. Thank you very much. I do appreciate you, especially coming so early in. And I think everybody did enjoy it at least. So I definitely want you to come on again sometime. Okay. Thank you very much again.
All right. Thank you very much. I'll check out. Thank you very much.
So thanks, man. And then I just want to say hi, thank you to everybody for coming. And then I don't know how to make it simple to this guy. He literally just validated measuring a flat plane. I don't know how much more I can explain it to him. So yeah, guys, thanks all for coming. Really, really appreciate you guys all coming. The power's about to go off. So see you guys all tomorrow night. It's going to be part 2 of the one I did last night on Fight the Flat Earth and Not a Professor Dave. PJ, what did you think of that quickly before the power goes off?
Oh, wow, just exactly what you just said there. Everything about that was begging the question, presupposed, and it was flat earth evidence. Simple as that, flat earth evidence. And he just didn't understand what you were trying to say to him. He didn't understand what you were trying to say to him at the end there. It was like, and we didn't talk over each other too much. He was like, no.
Look, I must say, I do respect the way he was, because I mean, other Globers talk over me constantly. So I do like the guy, actually. He's a bit slow on the takedown, because I try to explain the same type of argument in so many different ways that make my head hurt. He's a nice guy. Maybe he can watch this over again and over again until he finally gets what we're trying to say.
I'm sure. Well, maybe he will. But I think Lumpy came to the conclusion that he was insane. So.
But thanks all for coming. The power's about to go off. You guys are awesome. Really appreciate it. Thank you for all the super chats. It's a real blessing to the show. And then we'll see you guys all tomorrow. Cheers, guys. Cheers, PJ.
Good night.